Thanks, over to you.
Not a problem, thank you very much. Hi, I'm Brian. The introduction introduced me, so hopefully you know who I am now. I'd like to first acknowledge the Tomoki as the traditional owners of the land. This is something we do in Australia. Generally acknowledge the country that we're on. It's great to see the diversity of folks who are attending the conference, and it's just nice to be in this space where there's lots of new and exciting academic stuff happening. It really gives you a boost of energy. It's really fun. So today's talk, we'll be going through the ocean models that we've been using for climate assessment at CSIRO for the Australian Climate Service, and the funky problem that we've got ourselves into with regard to using unstructured mesh setups for optimizing our ability to do this work. I'm not a wave modeler. I can describe a few of the things that are happening in a wave model, but I'm no expert in the field. But my background is in surveying point cloud processing and earth obs. So I've been a historic user of big data, but this is a relatively new space for me. I've been in it for a couple of years. So my role in the team that I work in is very much a case of data curation and custodianship. So sourcing data forcing for wave models, ensuring that they're on vertical datums that are appropriate for, so that we get the appropriate water level information out of the wave models, and then forming data up for external use for external clients and putting on our data access portal. So coastal modeling team maps and models existing conditions through hindcast projects and projects future climate scenarios using all sorts of earth modeling, global climate model information. We have focus on coastal and littoral zones, and we look at not only inundation but compound effects, so interaction of storm surge, tide, wind wave, interactions, riverine flood, and certainly our upcoming work in this space will be focusing a lot on compound effects. But our initial work here is just an overall summary of the last 40 years in Australia for the Australian Climate Service. This information is relatively vital for communities for preparation for climate change. They're relatively interested, certainly in the Pacific. We have a lot of interested parties with regard to what are the likely effects of inundation in their lands, and how does that affect how they'll be able to use the land and their ongoing existence in these spaces. So yeah, we've done a bunch of Pacific projects. We worked with Vanuatu, and we've been doing climate impact vulnerability assessments for a few of the countries in the Pacific. And we have, of course, the work that we've been doing for the Australian Climate Service. Just want to highlight the Vanuatu Climate Futures Portal, which we did a bunch of work with NGIS, Beck, yeah. So yeah, and that's a really nice really nice front end web portal for accessing information with regard to varying climate scenarios and likely inundation and hazard into those countries, into those spaces. And we've been using that data ongoing to provide quantification of damage, impact, and economic impact of those scenarios. So that's been really vital work for these communities. So yeah, coastal models, they're really sensitive to geospatial scale. In the coastal extreme, in the coastal interface, you've got lots of complex bathymetry and geomorphology. If you were at Robbie's talk earlier, you saw some wonderful animations of the kinds of dynamic processes and interactions you see in the intertidal space. And there's lots of that, all those that dynamism shapes winds, waves, and currents in the area, and you'll have very complex. You're in the process of modeling complex processes in those spaces, trying to use that really fine data. So we prefer to model everything at really high scale, but we can't do that because the computational cost of running these models is massive, and we need to come up with ways so that we've got nice tight resolution at the coastline and much wider spacing offshore where the data isn't so important for the impact that we're trying to measure. And yeah, an orthogonal curvilinear model is not really efficient for the task. And this is just a couple of pictures of the early work that Mark Hertzfeld done at CSIRO with regard to adaptation of compass. So as you can see, you've got a model on the left-hand side of a rectangular bathymetry, I think that is, and then on the right-hand side here, you've got that sort of irregular grid where you've got much tighter spacing at the coastline, and as you move away from the coast, you've got less resolution. So you've got the ability to seamlessly transition between spaces. So what we're doing is we're doing modeling using an unstructured mesh. So for our CHAP schism work, we used, I think it was OCS mesh library to create a variable resolution unstructured mesh of triangles with about 500 meter resolution at the coastline. In some areas tighter than that, where we needed to maintain estuarine flow through river mouths and stuff, it was often down to 100 meters and up to 5 kilometers at the open boundary. There's a bunch of rules in the triangulation process to ensure that none of the triangles are super narrow or anything like that, so you get a realistic sort of surface. It gives us detail without needing to be massive, but it's not as easy to describe as 2D curvilinear, because your typical structure with regard to a netcdf file or something like that has 2D coordinate systems in it, and this file structure doesn't work with that. So this is a nice little picture of a Fa'atē in Vanuatu showing that variable resolution that we have for the Van Kierup work. And this was a schism coastal modeling product that we released with that work. So there is a standard for this made by the CF Standards folks. And it defines how you create the structure inside of your netcdf file or your Xarray file for describing the grid underlying. So we have a 2D grid for the work that we're doing in this particular project. It's 2D barotropic models. There's no levels in it, so our topology dimension is just 2, so it's 2D. So you create a variable with face node connectivity, so that's just an index of the nodes within the file. You have coordinate information for the nodes, and the face node connectivity links back to those coordinates. So this becomes a map for your structure of data within the file, and then of course your variable data is linked to the index of the nodes within the file. So it allows the structure of the mesh to be maintained so that you can, so that you don't have to retriangulate anything or anything like that. Essentially, it acts as a lookup table for something like QGIS or Pipeplot or something like that to go and reconstruct the structure. And it's part of the CF standards and metadata as of CF110. So that's great. That means it's part of compliance checkers and all of that sort of stuff for our outputs. And it makes it really easy for us to ensure that we're doing the right thing when we put together our files. So this is the UGRID standard page with regard to the definition of meshes. And this goes through like edge dimensions and face dimensions, and coordinates, and all of that sort of stuff. So you can put variable information on your faces, on your edges, if you have flux or flow between the shapes in your unstructured grid. Some models will model on the face rather than on the node. So you can, the standard gives you the flexibility to be able to portray the data in the file however you want. And we typically use Xarray. This is a standard schism grid file that we output. I think this is for, this is for chaps. And you can see the schism H grid variable, which has no data in it. It's just a list of attributes which describe that has the topology information in it. And that CF role mesh topology is the thing that the file interpreters look for to say that it's the structure of the H grid, and then it uses all of that information to construct the mesh within whatever viewer that you're using. So a little bit about Schism. It's a wave model and it's not. There are a bunch of inputs that you use into Schism, and I can give you this horrendogram, which is, it's a model you can use for all sorts of things. You can use for storm surge wave currents, tsunami hazard, sediment transport by geochemistry. It can do lots of stuff, but essentially what we've put into it is wind information, waves from our wave hindcast, tide information from TVXO, and water level information from ORS5, and winds from Barra R2, I think, as well. So all of these inputs come in as forcing data at the boundary, and then the model itself handles everything that happens inside of that boundary to come up with a facsimile of the conditions at any particular point. So CHAPS is our ACS coupled coastal hazard prediction system. It's an unstructured grid model of the Australian coast, 1.4 million nodes, but with that tight spacing at the coastline and variable resolution out to the edges. We do have it running inland up to the 12-meter contour, but that is, of course, that could be anywhere from inside of half a kilometre away from the coast to dozens of kilometres inside, depending on whether there are floodplain areas, estuarine areas, and all of that sort of stuff. So we use some trickery in QGIS for variable buffering to create a variable buffer based on this 12-metre contour, so that we weren't coming too close to the coastline in areas that we had really steep topography. We got a 40-year hindcast from 81 to 2020 with hourly bulk wave parameters plus wet-dry flags. The Schism output itself is not CDF compliant, and I've put an asterisk there because they have fixed that recently. But as of the point of the production of this model, it was not. So that's a bit of a map of the CHAPS grid over Australia, and you can see the extra levels of detail that have been put into places like the GBR, for instance, where the water's pretty shallow, and we wanted to get a really nice sort of account of what's happening in those sorts of areas. And this is just a comparison to the grid from the Corker hindcast, which is our current wave model hindcast in the Australian area and surrounds. And that just gives you an indication of the improvement of scale that we're working with in these sorts of areas. It's just some nice, pretty pictures that I've put together over time for this sort of stuff, showing various parts of the mesh around the coastline of Australia. So UGRID helps us to recreate this, but we have other problems with CHAPS data. For instance, it's a large data set. The raw data set was somewhere along the lines of 100 terabytes, and it's really not easily serviceable for people to use. So we did a bunch of rechunking and re-encoding of the data. we came up with some spatial reordering of the points in the grid. So the picture on the left is how it comes out of Schism with regard to the node ordering, and we did a bit of playing around with H3 grid to reorder the points in the model so that we've got some sort of semblance of sense. When you want to do a spatial query of an area in the grid, you don't have it trying to get chunks from everywhere. Hopefully, with this sort of regridding, you're getting it from a specific clump or chunk within the data. This process has given us a real improvement with regard to file access and retrieval. So for instance, doing a single node slice through time for, I think this is for a year, used to cost, actually no, this is for the entirety of the 40-year time series. No, I think it's just for a year. It used to cost us 7 minutes and 11 seconds because the native chunking of Schism comes out in time steps. So you would have to load half of the entire data set to get one node of time series information. We got that down to less than 1/10 of a second. So that was really a really big improvement for usability of the data for specific chunk queries. So QGIS will ingest UGRID data, and we've got it to run on smaller models like the Van Curup dataset. So this is HS, so this is significant wave height for a period of 2011 for Vanuatu. So this is a 200,000 node grid. So we've managed to get QGIS to load in depth information, but not necessarily animation information, because we've got some issues with regard to the rechunking and re-encoding of the data that make it a little bit less friendly to QGIS. But it's still like for the smaller data sets and the the ones that have been less played around with regard to compression, it works rather well. So. We also do things the old way with PyPlot, create animations and all that sort of stuff. I got some lovely little animations of, this is a smaller grid off of the Great Barrier Reef. And the left one with the elevation of the currents, you can see that nice sort of, the tidal currents moving off phase in Broad Sound, for instance. And these are really nice ways of visualizing the data that's in there. The wave model has kind of lost their mind when we actually got to this point. They could quite easily spot issues with regard to the elevation information, the water levels in the model and all of that sort of stuff. And they could see that the currents were working in the way that they expected. This is an East Coast low in 2007. You can see that big blob of wave action, wave energy in that sort of area, and then the energy gradually comes out of the system, and the period is shown on the right, gradually decreases. So the wave models love it. It's really cool. Thank you. So there are other ways of looking at the data. Terria will handle UGRID data. It's a bit clunky with regard to symbology and all of that. The folks in Coastal Environment Modeling team have the EMS suite, which is a library, EMS array, which you can do transects and other analysis. We've got the Pykea library, which is an effort of ours to link Schism data to observation data like wave buoys, tide gauges, and such, and to do nice time scale plotting things and provide that sort of sense of that the model itself is producing the right numbers. And Move is coming soon, which is a full standalone visualizer of UGRID data along with other model data, and it provides a nice little interface with proper JavaScript and all of that sort of stuff. I will very quickly talk about WAX. WAX is our wave hindcast. It's global. It has an SMC grid. It has all these variables, and it has good detail around New Zealand as well as Australia. and it's used as forcing. It's on an SMC grid, which is a different kind of UGRID, which I'm not going to talk about today, but yeah. There's issues with visualization of that as well, but it's for another forum, I guess. Where do I get the data? Chaps at Wax are available in the DApp at these QR codes. There are also example notebooks that we've come up with for using the data visualization, all that sort of stuff. So the tools are there. Feel free to get your hands dirty. And I've got lots of people to thank, of course. But the most important one is you.
Okay, question time. Anybody? No? Stunned silence.
That's cool.
They want to go to lunch.
Yeah. I don't blame them.
All good? So they can find you around at lunch?
Yeah, I'll be around all week, so yeah. Yeah.
Some people get very shy at these things. So, with that then, I would like you to join me and thank him again.